Originally, when I was an undergrad, I really wanted to make an artery. So tissue engineering when I was an undergrad was like the next new thing. We were going to be growing organs in dishes all the time. As I got into it, I realized that we didn't know enough about how they were made in the first place, and we're still learning. I'm Jessica Wagenseil. I'm an associate professor in mechanical engineering and material science, and I'm also the director of the PhD program. So we study vascular mechanics, and we focus on the large elastic arteries such as the aorta, which is the largest artery that carries blood away from your heart. We're interested in elastic fibers, which is what allows them to expand and relax every time your heart beats. And we study basically three areas. One, how they're made, right? So how the elastic fibers are laid down to give them the right mechanical properties. And we study defects in the elastic fibers that lead to aneurysms, which is a dilation of the artery that can eventually rupture or dissect. And then we study how defects in the elastic fibers lead to increased stiffness, which causes hypertension, which is a huge cardiovascular problem in the US. So Austin is testing mechanical properties of a newborn mouse aorta. And the mouse has a genetic defect in elastin, which is the main protein that we study. And what we've done with this genetic defect is actually we can control which cells are making the elastin. And so we want to know in the vessel wall which cells across the wall are really making the elastin and how that contributes mechanically. The repercussions would be if we know which cells are making the elastin, we can perhaps control it better, right? So help those cells make more or make less. And then also, if we know that elastin is really important just at the inner layer or just at the outer layer, we could perhaps target treatments to help make elastin and change the mechanics in those places.
So with my project in particular, we're investigating how drugs and molecules transport across the arterial tissues, and specifically how changes to the arterial tissue can affect that transport. And the ultimate goal of the project is to better contribute our overall understanding of how drugs can transport from point A to point B within the tissue and hopefully lead to better therapeutics for cardiovascular disease. So
the cardiovascular disease is the biggest motivating factor. So that is the largest killer in the US. And then we're interested in both addressing the disease and then also understanding how these things are made so that we could someday make replacement arteries like in tissue culture in the lab.
My background is in aerospace, so the research I'm doing here with Dr. Wagenseil is based on computational fluid dynamics. So I have that background in aerospace, which I work with different computational fluid dynamic software. So I try to implement that knowledge into a cardiovascular concept. So I try to model the cardiovascular of mice and then see the fluid and solid interaction based on the computational methods.
There's some places where it's more competitive than collaborative, but here, everyone I've talked to wants to know how they can help and how we could work together, either at the med school or different departments within engineering or even outside of engineering.